Hey there, kids. It's time to talk about plate tectonic theory. That's your notebook. Here we go. What would you get if you crossed Alfred Wegener's continental drift and Harry Hess's seafloor spreading? Well, remember, Harry Hess seafloor spreading, that's like the conveyor belts. And what would Alfred Wegener think if he knew about Harry Hess's idea about seafloor spreading? Because it is the perfect mechanism. It is a perfect mechanism for moving these continents around. Let's take a look at what I'm talking about. Let's take a look. Now, let's remember that Alfred Wegener noticed that the pieces fit together like puzzle pieces of the continents, and he proposed that it took millions of years to break those continents apart into their present position. And if we were to go looking for what the mechanism was and where it was happening at, okay, oh, by the way, let's not forget the evidence that Wegener used about fossil correlation and strata, the rock layers, and as well as other pieces of evidence. He had also the correlation of paleoclimate data as well. Let's not forget that one. So, but what did people think when they heard about Harry Hess's idea? They didn't like it. He's like, well, don't worry, Moby, it's because they didn't have a mechanism. But we now know what's going on. In the Atlantic Ocean, there's a mountain range we call the Mid-Atlantic Ridge. It's an underwater mountain range. And that's where the continents are pulling, this is the source of seafloor spreading. They're looking for it right now. Tim and Moby are looking for the magma. All right. He had no way of proving it at the time, but we now know because of Harry Hess, he had some evidence. But we know is that the Earth today is divided into the core, the mantle, and what we now are going to call the crust. Now, the upper part of the mantle is called the lithosphere, and the lithosphere and the crust move on top of the rest of the mantle, primarily the asthenosphere, which is the part that it moves. Notice these over here, these are dividers, are the plate boundaries, and the motion moves, it all moves very much like how water boils, and this is called a convection current. And this convection currents are the force that drives apart and drives the theory of plate tectonics, and it actually ends up moving the continents apart from each other. All right, so let's go back to our slideshow. There's your hook. I'll be wondering why I didn't give you Tim and Moby. I've been watching everyone. It's there on the internet. All right, so we've got 12 major plates on Earth's crust. We got 12 major plates. Let's see if we can count them up, right? So let's see. Let's start with where we live, and let's take a look. First of all, there's continental crust, and then there's oceanic crust. The continental crust, which is right over here, like in North America, we can see the continent. We can see the continent is dry land, all right? And over here we have Alaska, we have Canada. Down here's California. That's like Alaska and Oregon right there. Here's Mexico, Florida. Moving on up, this is like Nova Scotia. Here's Greenland. So this is a whole thing is called the North American plate. Everything that's brown, this tannish brown, the darker is oceanic crust. The oceanic crust is thinner than the continental crust, and it's less dense. That's going to become more important later. Let's see if we can count 12. North American plate, that's the one we live on. If we go to Half Moon Bay, we're standing on the Pacific plate. The Pacific plate is our next door neighbor. There's the Cocos plate down here. That's like down around the border of Mexico. There's the Caribbean plate. It's a small little plate. The Nazca plate, the South American plate. It's all purple. The Scotia plate. The Arabian plate is this yellow one. That's diverging right there, by the way, as well. There's another diverging zone besides here. There's the African plate, the Indian plate, the Australian plate. Are you counting? I hope we're almost done. We've got a few more. We got Juan de Fuca, we've got the Filipino plate, and then finally the Eurasian plate. Did you count 12? I wasn't counting. You can go back and count yourself. All right. So each plate is moving in a different direction, and the arrows tell us the directions they're moving in. They're either moving away from each other, at about rate of about 3 to 10 centimeters per year. They are sliding past each other, or they are converging. They are crashing in each other. In this case here, in this case here, in most cases where they're crashing in together, you might want to recognize some of the features that occur when you have colliding plates. Now that's so complex. We're going to be going into that in greater detail next week. We know about these plates. Well, we assume that the plates exist where they do because of three things. One's earthquakes, one's volcanoes, and the other one is where the mountains are. So all this came out originally in the 1950s and 60s during the Cold War when Americans were looking for evidence that the Soviet Union was testing atomic bombs. We now know about Earth's structure. Remember that we've got the continental crust. This is oceanic crust. So the crust will be the dark part. And in the lithosphere, all this other part is the mantle. So the mantle is broken up into three different layers: the lithosphere, the asthenosphere, and the mesosphere. So it's that three layers of the mantle. The lithosphere and the crust have been broken up into 12 plates, and they move over the asthenosphere because of mantle convection, moving the continents. And where they meet is called the plate boundary. There's three different ways that plates can interact. They can either move away from each other, which we'll take a look at in greater detail in a moment. They can slide past each other, where we actually happen to live. It's the San Andreas Fault. And when they move, we have an earthquake. Or they can converge together. And when they move, there's an earthquake. So whenever earthquakes occur, we end up having motion of plate boundaries, and I want to get more into that next week when we're talking about that very topic. I have one last video for you guys. We're going to just kind of run through it quickly. I think I have it once again on hyperspeed. Please, let's go. Oh, that's continental drift. I don't want that. Come on. Go back. I had it all set up for you too. Okay, here we go. Plate tectonics. Good. It's moving. Super fast. Perfect. That's what we want. We want to go in fast. All right, so the whole idea of plate tectonics, once again, is merging the two things between seafloor spreading and continental drift. Let's remember the lithosphere has been broken up into plates. We're over here in the green. It shows us our plate boundary. The different colors are telling us what's happening at those boundaries, if they're converging, diverging. So green must be a divergent plate boundary. The asthenosphere and the lithosphere are part of the mantle. The lithosphere and the crust are what been broken up into plates, 12 major plates. Continental crust, is shown here, is far thicker and breaches into the lithosphere more than the continental crust. Also, the continental crust is a lot less dense, which means that if continental crust and, well, the lithosphere that includes continental crust converges with the lithosphere that does not have continental crust, then one's going to go under the other one. We're going to get a subduction zone. So, but remember, right now we're really dealing with divergent plate boundary and that driving force of convection, the convection currents in the asthenosphere that drive the plate motion. So this would be the lithosphere. This brown part would be lithosphere. This would be the crust, the oceanic crust that's being generated at the mid-Atlantic ridge. And we're actually right here in this little rib zone. Let's remember the plate boundary features. And the arrows over here indicate if they're converging, diverging, or if they're transform, right? So we can actually see there's actually 4 different trends. I like the colored features on this. A little easier to see which one is which. There's 3 different ways that plates can interact. We happen to live right next to one where they're sliding past each other. Fascinating as it is. Now, why do we know this? First reason, earthquakes. That's purple. But also there's volcanoes, chains of volcanoes, and where mountains are currently being built. That is how we assume where we know where these boundaries are. Like, for instance, the Himalayan mountains down here. All right, so plate boundaries we'll be talking about more so next week. But the one I want to get into just a little greater detail as we wrap up our discussion over here is the Mid-Atlantic Ridge out here in this region. I'm gonna have you guys probably watch this entire video next week as part of the line. However, the divergent plate boundary is what we studied last week, so let's talk about it now. Great image here. Once again, we see the lithosphere mantle and the asthenosphere. These are all part of the mantle. And then we got our crust. This is the continental crust. This is the oceanic crust here. And we have the motion, the arrows, the vectors are representing the fact is that there's a force ripping the thing apart, causing motion. The Mid-Atlantic Ridge and the newly formed seafloor, all right, are being shown over here as the mantle, as the asthenosphere moves into and through the Earth's crust, moving the lithosphere and the crust with it. Remember, the lithosphere and the crust have been broken up into about a dozen different plates. The mid-ocean ridge is the place where all this is happening in terms of the actual where we know that the magma from the asthenosphere is bridging through the crust and actually driving seafloor spreading. Now, how do we know this? Once again, this is from last week. We got the seafloor magnetism, that north, that the domains are aligned to the North Pole and for normal. Then we got the reverse polarity when they align to the south. So that's one thing. Plus, we got this age of the seafloor rocks being so much different, that the newly formed are a lot younger than the others. All right, so this is the theory of plate tectonics. I'll have you guys going into greater detail with this next week. Hope you enjoyed the slideshow, and I hope you enjoy your week in science.